Here is another question based on work, energy, and power. The diagram below shows a boy skateboarding on a ramp which is inclined at 20 degrees to the horizontal. This is the angle. I like to call it angle beta. A constant frictional force of 50 Newton acts on the skateboard as it moves from point P to Q. So the frictional force is here. Let's write down the data. So we're given the frictional force to be 50 Newton. Consider the boy and the skateboard as a single unit of mass 60 kg. So we're given the mass 5.1. Draw a labeled free body diagram showing all the forces acting on the boy skateboard unit while moving down the ramp from P to Q. So our free body diagram must be based on this slope here or on this surface. So let's say the object is here. We're going to have N, we are going to have a weight W, and we were told that there's friction. This is your F. So this is it. Now we know we can rewrite this free body diagram in component form of the weight. Now let's do that. Friction and normal force. But as for the weight, we are going to have the perpendicular weight and the parallel weight, which are components of the weight. Now that we have included these two, we are not going to include this weight. Therefore, these two free body diagrams, they mean the same thing. Let's continue. Points P and Q on the ramp are 25 meters apart. So we can add on our data that our change in X is 25. The skateboarder passes point P at speed V initial. So we are not given the initial velocity, is what we'll be looking for. And passes point Q at a speed 15 meters per second. So 15 meters per second is the speed at point Q. Okay, state the work energy theorem in words. To state the work energy theorem in words 5.2, we are going to use this formula to state the work energy theorem. We just convert it into words. Now, the net work done on an object is equal to, that is this part here, the net work done on an object is equal to, the change in the object's kinetic energy is this part. So the work energy theorem is going to be stated in this way. 5.3. Use energy principles to calculate the speed V initial of the skateboarder at point P. So according to the work energy theorem, we need to know the forces that are on the object. So we are going to use this free body diagram. In this free body diagram, we are only going to consider the forces that are doing work on the object, which are these forces. Perpendicular forces, they do no work. Hence, this force, which is the normal force, and the perpendicular weight are not going to be included. We know that the work done on an object is given by the following formula. So we are going to have the work done by frictional force plus the work done by the parallel weight is equals to the change in kinetic energy. Now, for this part here, we are going to substitute this formula. Okay, so we have the frictional force, which is our F. Now, the displacement cos theta. We are going to do the same thing for this part here. Now, this is what you have to know. The parallel weight is given by mg sine beta. Beta is this angle here, the angle of the slope. Now, The perpendicular weight is given by mg cos beta. And hopefully you know that the weight itself is given by mg only. Now all these are the forces. These are the components of the weight. Okay, so this means that instead of our force, we are going to have mg sine beta. Now we are going to have this part here. So we are going to have this being equal to the change in kinetic energy. So the force we were given that it's 50 Newton. We are also given that the displacement in which this force acts is 25 Newton. Since this is friction, friction is always opposing the motion, hence we have 180 degrees. The mass we were given that it is 60 kg. We have 9.8 sine of 20 degrees. This is 25 cos. Now you can see that this boy is moving down the slope, and mg sine theta is a force that is pointing down the slope. You can also see it here. They are pointing on the same direction, hence the angle between them is cos 0. This on a calculator, you are going to get 3777.696. It's equals to the change in the object's kinetic energy. Now we know that we can rewrite this part. So we know that the change in kinetic energy could be written as the final kinetic energy minus the initial kinetic energy. This is going to be 1 over 2 mv squared final minus 1 over 2 mv squared initial. Putting everything together, we are going to substitute this here. So we are going to have being equals to 1 over 2. Instead of the mass, we know the mass is 60. The final velocity we were given that is 15. So we want our initial velocity. So if you punch this on a calculator, you're going to get 6,750 minus 1 over 2. Now we want to take this to the other side. So you're going to subtract 6,750. If we subtract this, the other side, you're going to get negative 2972.304. This is going to be equals to, if you divide 60 by 1 over 2, you're going to have 30 v squared initial. Now we divide both sides by 30. We get that v initial squared is going to be equals to 99.0768. Now you take the square root of both sides. You're going to get 9.95 meters per second. 5.4. Calculate the average power dissipated by the skateboarder to calculate the average power dissipated by the skateboarder to overcome friction between P and Q. So they want us to calculate power. We know we have two formulas to calculate power, which is this one and this one. Now we can see that we do not have the time, and we also do not have the average velocity. But we know we can easily find the average velocity. There are two ways to find the average velocity. The first one is this one, which you might probably be knowing right now. Now we cannot use this way because we don't have the change in time. The second one is to use the final velocity plus the initial velocity divided by 2. We do have the final velocity, which is 15. The initial velocity, we calculated it here. So it is going to be 9.95 divided by 2. And this is going to give us 12.475 meters per second. So you can come here, we have the frictional force to be 50 Newton, and then the average velocity, this is going to give us, now let's try to use this formula and see if we can get the same answer. So we know that the work done by friction is given by this formula here. We do not have the time. To calculate change in T, we can use this formula here. So where we have the final velocity plus the initial velocity divided by 2 multiplying by the time. Now, so 25 is our displacement, and we have this part. We are going to put it's this one here. So we are going to have change in time. So we will divide both sides by 12.475. Is going to be equal to, now we have our force to be 50, the frictional force we have 25, and then it's cos 180. We are going to divide this by our 2.004. Now if you punch this on a calculator, you are going to get 623.75. So your final answer, you will say that the power dissipated by this frictional force is 6.2375 watts. That's it for this question. Like, subscribe, and share the videos for more similar content.